Hello students, continuing with number system, let us look at certain special properties of rational and irrational numbers. I have listed them over here. So the first one, every rational number can either be terminating decimal or non-terminating repeating decimal, right? So we had seen in the previous examples that when we were dividing rational numbers, taking the decimal points, either the quotient terminated and we got a remainder as 0, or the quotient, the block of numbers kept repeating in a cycle. For example, 1 upon 7 was 0.142857 and 142857, then again 142857. So the block 142857 kept on repeating, which is what it means by non-terminating repeating decimal. Then vice versa, to this statement we have other two statements. Every terminating decimal is a rational number, agreed? Similarly, every repeating decimal is a rational number. So terminating decimals would be rational numbers and repeating decimal, non-terminating repeating decimals would also be rational numbers. Now let's come to irrational numbers. Irrational numbers are the opposite of this. So an irrational number can neither be terminating decimal nor a repeating decimal. Agreed? Now the last 2 points hold a lot of importance, especially when you have certain questions in your papers that write some irrational numbers, write some rational numbers. So if you are confused how to write an irrational number, these two statements are going to prove in very handy. So let us read this slowly. The square root of any prime number is an irrational number. So any prime numbers are numbers that are divisible only by themselves or 1. Okay, so prime numbers are 2, between 1 to 10 for example are 2, 3, 5, 7, and after 10 you have 11, 13, 17, 19 and so on. So all these are prime numbers. Now if I take the root of these numbers, square root of these numbers, whatever answer we get for root 2, root 3, root 5 or root 7 and so on, they are all going to be irrational numbers. Okay. So if you asked for a question in your exams, give few examples or give 2 or 3 examples, give 2 or 3 examples of irrational numbers, you can easily remember this and accordingly write your answers. So I hope you've got an idea how to write irrational numbers. Now other two points are also very important. If m is a positive integer, so m is a positive integer as in it would be all the numbers on the right hand side of your number line, but not a perfect square, then root m is an irrational number. So what are examples of integers that are not perfect squares? We have 1, but 1 we have the square root of 1 as 1. We have positive integer, not a perfect. We have root 2, you have root 3, root 4 is a perfect square, so root 4 is going to give you 2, so that is not going to be irrational. Then we have root 5, we have root 6, then we have root 7, then we have root 8, not root 9, because 9 is a perfect square and square root of 9 is going to give me 3. So not 9, root 10, then root 11, root 12 and so on. So square roots of positive integers that are not perfect squares are irrational numbers. Got the idea? Similarly, for cube roots, if you have positive integers, okay, which is not a perfect cube, then cube root of m is an irrational number. So if m is a positive integer but not a perfect cube, then cube root of m is an irrational number. Let me give you an example. Perfect cube, root 2 is not a perfect cube, 2 is not a perfect cube, 3 is not a perfect cube, 4 is not a perfect cube, 5 is not a perfect cube, 6 is not a perfect cube, 7 is not a perfect cube, 8 is a perfect cube. Why? Because 2 cube is 8, so not 8. Then you have 9 not a perfect cube, 10 not a perfect cube. So when you take cube roots of these numbers, cube root of root 2, cube root of 2, cube root of 3, cube root of 4, cube root of 5, and cube root of 6, 7, 8, 9, 10, these are all going to be irrational numbers. So now for example I have 27. Is this an irrational number? No. Why? Because we know that 27 is 3 into 3 into 3, which is 3 cube. So 27 is a perfect cube. So cube root of 27 is not an irrational number. Similarly, if I give you 64, Cube root of 64 we know is 4. So 64 is a perfect cube, therefore cube root of 64 is not an irrational number. So with this we have learned certain very important and special properties of our rational and irrational numbers. Let us not waste time and proceed with exercise 1.3 of number system. Let's take a look at the first question. Write the following in decimal forms and say what kind of decimal expansion each has. So the first there are two statements in this question. First of all, we need to convert these fractions into the form of decimals, and then you have to state what kind of decimal expansion it is. We have learnt three kind of decimal expansion. One is wherein we have a terminating decimal, then we have non-terminating but repeating decimal. These two hold for rational numbers, and the third one was non-terminating and non-repeating decimals. So let us do the calculations and find display these numbers into decimal forms and also say, mention what kind of decimal expansions they are. Okay. So the first one, 36 upon 100. 36 upon 100 can be, we have, see, let me write it clearly for you. You have 36 upon 100. We know that there are two places in the denominator, that is two zeros over here. So I can simply take one place, two place, starting from my right, moving towards my left, two places, and place a decimal here in order to get rid of this 100. So 36 upon 100 is nothing but equal to 0.36, right? So if I wanted to convert my 36 into remove this decimal, I would multiply it with the 100. Similarly, I have 36 upon 100. Okay. So this was a very simple one. These are not difficult. I am not saying that this one is simple, that implies these are difficult. These are not difficult, but you need to pay attention and solve it very neatly, clearly, and pay a lot of attention while solving these sums. Okay. Let us take a look at the second one, 1 upon 11. Okay, before I solve 1 upon 11, this was 0.36, right? We need to mention what kind of decimal expansion it is. So since our decimal is terminating over here, there is no digit after 6 nor there is a bar, right? So this is neither repeating. So this is the decimal expansion is terminating, or this decimal expansion is terminating decimal. Okay. So please take a note of this, because I am going to erase the board, just this section. Okay. The second one is 1 upon 11, or rather should I just erase the board on the right hand side on my, and we will solve it more neatly. We will only write the answers over here. So this was 0.36 terminating decimal. Okay. So this one is solved. Let's take a look at 1 upon 11. So 1 is my dividend and 11 is my divisor. Now 11 won't divide 1, so I put a 0 here, 0, and I get 1. I am going to put a decimal here and add few number of zeros. Okay, I can add as many zeros as I want after the decimal. It means only 1. Okay, 1.00000 until infinity is 1. So now I take down this 0 and I put a decimal here. Again 11 won't divide 10, so I put a 0, 11 zeros are 0, 10, I bring down this 0. Now we know that 11 nines are 99. I am left with 100 minus 99, which is 1. So I bring down this 0 now. 11 won't divide 10, so a 0 here. So 11 zeros are 0. I am left with 10, I bring down this 0. Again 11 9s are 99. I'm left with 1. I bring down this 0. Let us add more zeros. So 11 can't divide 10, so 0. I'm left with 10. I bring down this 0. Pointing this arrow here. So 11 9s are 99. So do you see a repetitive pattern here in the quotient as well as in the remainders? I have a 1 here, then 1, then 1, then 1, 1, 1. So the quotient is 0.090909. So I can write 1 upon 11 as 0.09 and a bar on 9. Why bar? Because 09 is repeating. Therefore, what kind of a decimal expansion it is? It is a non-terminating repeating or recurring decimal expansion. Got the idea? Let's go. So I tick this. Okay. I'll go ahead and solve the third one, which is a mixed fraction 4 1 upon 8. So we will first convert 4 1 upon 8 into a proper fraction. So 4 1 upon 8, we know that 4 1 upon 8 can be calculated as, I put a multiplication sign here and an addition sign here. So 8 4s are 32 plus 1, 33 upon 8. So I have converted 4 1 upon 8 as 33 upon 8. Now let us go ahead and divide this. 33 becomes my dividend and 8 becomes my divisor. Now let us check whether what would go in 33. 8 4s are 32. I am left with 1. I put a decimal here and add few number of zeros. And again I add a decimal over here. I bring down this 0. 8 1s are 8. So 10 minus 8 is 2. I bring down this 0. So 8 2s are 16. 20 minus 16 is 4. I bring down this 0. 8 5s are 40. So I got my remainder as 0. I do not need these zeros anymore. So what is my quotient? 4.125, and it is terminating because my remainder is 0. So the answer to this one would be 4.125. And what kind of decimal expansion it is? It is a terminating decimal expansion. I am just writing terminating instead of terminating decimal expansion. So let us go ahead and solve 3 upon 13. I'll tick this sum because we have completed it. So 3 upon 13. 3 becomes my dividend and 13 becomes my divisor. Now 13 obviously won't divide 3, so I put a 0 here and a decimal point here, and I add a decimal point here as well, and few number of zeros. Now 13 2s are 26. So 30 minus 26, do not consider this as 3.0 while you are doing it. This point is only to denote that we are adding extra number of zeros, and it means 3.00000, which is nothing but 3. But while calculating, we take this as 30. Alright. So 30 minus 26 gives me 4. I bring down this 0. What do I get? 13 3s are 39. 40 minus 39 is 1. I bring down this 0. 13 won't divide 10. So 0. 13 zeros are 0. I am left with 10 and I bring down this 0. Now let's check 13 into 5, 5 3s are 15, 5 1s are 5, 65. 13 into 7, 3 7s are 21, 7 1s are 7, 8 9. So 13 7s are 91. I am left with 9. 100 minus 91 is 9. I bring down this 0. So let's check. 13 6 are 3 6 are 18, 6 1s are 6, 7. So 78 and 91. So I am going to take 6. 6 are 78. This is going to be 2 and 8 minus 7 is 1. So 12. I bring down this 0. Now 13 into 9. 9 3s are 27, 9 1s are 9, 10, 11. So 117. 13 9s are 117. I bring down this 0. Then I have 13 2s are 26. Now if you notice, we have 3 here and 3 here, and then 4 here and 4 here, which means that this sequence of remainders, that is 3 4 1 1 3 4 1 1, then 10 9 12 is going to repeat. So see, this will be similar to 2 3 0 7 6 9, again 2 3 0 7 6 9. So these terms are going to repeat, right, in a pattern. So 3 upon 13 is equal to 0.230769, and I put a bar on top of 230769 because these digits are going to repeat, which is my decimal expansion would be non-terminating and repeating. So this is non-terminating and repeating. So I'll tick this. Let's go ahead and solve 2 upon 11. So 2 is my dividend, it goes inside, and 11. So 11 zeros are 0 because 11 can't divide 2. I put a decimal point in my quotient as well as in my dividend, and I add a couple of zeros to my dividend. And now I bring down this 0. 11 ones are 11. So 20 minus 11 is going to give me 9. And I bring down this 0. 11 8s are 88. 90 minus 88 is going to give me 2. I bring down this 0. 20. 11 ones are 11. 9. I bring down this 0. 11 8s are 88. So do you notice something now? The quotient, the blocks of digits in the quotient, that is 1 8 1 8, is repeating, as well as these remainders 2 9 2 9, they are repeating. So my rational number becomes 0.18 bar. Why 18 bar? Because 18 is repeating after the decimal. Therefore this is a non-terminating repeating decimal expansion. Let us tick it. Finally, the last sum of this question of exercise 1.3 looks like a big number, 329 upon 400. But let's see how quickly we can solve it and how simple it is, right? So I have 329 as my dividend and 400 as my divisor. Obviously 400 cannot divide 329, so I'll say 4 zeros are 0 and I bring down 329 as it is, and I add a decimal to my dividend as well as to my quotient. add a couple of zeros to my dividend so that we can do the decimal expansion. I bring down 1 0. So 400 into what would give me 3290? Let's check. 4 3s are 12, 4 4s are 16, 4 5s are 30, 4 6 are 24, 4 5s are 4 8s are 32. So 400 into 8 would give me 3200. So I'll say 4 8s are 3200. I'm left with 90, right? I bring down the 0. 400 into 2 is going to give me 800. So I'm left with 100 over here. I bring down this 0. 4 2s are 8, again 800. 400 into 2 is going to give me 800. So minus 200. I bring down this 0. I have 4 5s are. So 400 into 5 is going to give me 2000. If you want, you can confirm it. 400 into 5. 5 zeros are 0, 5 0 0, 5 4s are 20. So 2000. So I got a remainder as 0. Therefore, I do not need these zeros anymore. And my calculation has terminated. I have a definite quotient because I got a remainder as 0. So therefore, the answer to this would be 0.8225. And what kind of decimal expansion it is? It is a terminating decimal expansion. Please take a look. So you saw how we have expanded various rational numbers and mentioned what kind of decimal expansions they are. So this was about it. We will continue with the rest of the exercise in the next class. Thank you.
Hope this video increased your knowledge. For more such videos and a completely free educational content, log on to www.epathshala.org or visit our ePathshala YouTube channel. We have each and every question solved for maths, physics, chemistry and biology. So subscribe our channel, share with your friends, like our Facebook page and follow our Twitter handle for regular updates and important educational tips, and also win ePathshala goodies. So what are you waiting for? Subscribe this channel and enjoy the freedom of education.